We previously discussed the input impedance Z in scene when an arbitrary load ZL is connected to a line of arbitrary length L and characteristic impedance Z0. Now let's examine some specific scenarios. The first one is when the ZL connected at the end is precisely the same as Z0. In this situation, the input impedance Zin of D observed from any position D when looking to the right is always Z0 and ZL, because the numerator of Zin equals the denominator. When ZL is equal to Z0, gamma 0 is ZL minus Z0 over ZL plus Z0, which will be equal to 0, indicating that no refraction will occur. Consequently, regardless of the line's length, there will be no transmission line effect, meaning there will be no impedance conversion effect. In the RF field, a low impedance of 50 ohm is a typical value. Hence, when designing a layout, the line impedance is often set to 50 ohm. This is because when ZL is equal to Z0, there will be no transmission line effect, regardless of the line's length. Now let's consider the scenario when ZL equals 0, that is, when the terminal is grounded. In this case, gamma 0 equals -1, indicating that the incident wave is entirely reflected. The angle of rotation when the incident wave is reflected is 180 degrees. In this case, the input impedance of a shorted line viewed from any position D is J times Z0 times tangent beta D. This result demonstrates that even when the terminal is grounded, the ground is still converted to an imaginary impedance. However, we must recognize that the impedance of a shorted line is reactive. This means that by adjusting its length, we can convert a shorted line into an inductor or capacitor, which is a remarkable feature. In RF circuit design, we must exercise caution, since a grounded line may no longer be a perfect ground. For instance, the grounded line of a transistor may become an inductor at a certain operating frequency, causing degeneration and reducing the amplifier's performance. Now let's examine what occurs when the end of a line is connected to an infinitely large load, that is, the end is open. In this situation, gamma 0 equals 1, indicating that the incident wave is entirely reflected. The input impedance is -J times Z0 times cotangent beta D, which shows that even when the line's end is open, it still converts to a reactance. We must also pay attention to this, since an open line may no longer be a perfect open circuit. We can also see that the impedance of a shorted line and an open line is linked to the tangent beta D and cotangent beta D functions. At some unique angle, the values of these functions will tend to positive or negative infinity, and at some specific angle, the value of these functions will be exactly 0. This fact suggests that we may also benefit from it. In our next video, we'll examine the implications of these specific line lengths.